Hey everybody, Kyler Petrick here. I'm joined with Daniel Spiegelman, James Maxwell, and Corbin Schreiner. Today we'll be looking at and analyzing case study number 6. In this presentation, we will cover our introduction, the problem in the case study, solution number 1, which will be a construction, solution number 2, which will be about rerouting the hole, and solution number 3, which will be an agronomic change. After that, we will look at the who-out equation, a summary, and our bibliography. In this project, we meticulously analyzed the drainage problem affecting a golf course tee box, recognizing its impact on the overall playing experience and course maintenance. Our investigation involves studying the topography, soil composition, and existing drainage infrastructure to gain comprehensive insights. Through thorough research, we aim to propose 3 innovative solutions tailored to address the specific challenges posed by the site. We will first look at a construction solution, then move into a rerouting of traffic solution, and finally finish on an agronomic solution. By combining practicality and sustainability, our goal is not only to resolve the current issue, but also contribute to a long-term resilience and performance of the golf course. The wet tee issue on the rear tee deck is multifaceted. The severe compaction and slow drainage suggest poor water infiltration. Factors contributing to the wet conditions include the nearly flat terrain, an access point depression, and the sandy loam soil behind the retaining wall, possibly restricting water movement.
Hey everybody, Dan here. In the coming slides, I'll be introducing our first solution, which will cover a reconstruction of the tee box, and I will describe the management strategies and cost analysis. Management strategies. First off, to fix the drainage problem of water being fed down from the back of the tee deck and it not draining properly. The first step would be to analyze the slope of the tee deck. Once that's sorted out, you will then use a sod cutter to take up all the sod and take that away. You'll then have to start the excavation process and put the big O and a drain in during that process. The big O will be placed facing or going towards the front right of the tee deck. Then the drain's going to be just off the edge of the tee deck. Once the excavation process is complete and everything's put into place, you'll then start the reslope process of the tee deck so that the water from the green will drain towards the front right side of the tee deck. After the resloping's done, you'll need to put 2 slightly angled troughs going along the back and side walls, so all the water coming off the wall can go directly off the tee deck. Cost analysis. For premium Kentucky bluegrass sod, you'll be paying about 50 cents per square foot, and we'll need 300 square feet of sod, so you're paying roughly $150 pre-tax. Then for the big O pipe, we'll need approximately 55 feet of it, so we'll need to buy a roll that is 100 feet long, which costs about $149 pre-tax. Then for the catch basin, or the drain catch basin, we'll be going with the RELN 13-inch square catch basin kit, which is going for $90.56 from Home Depot, which brings the overall cost to $389.56 since all the work will be done in-house.
Hi, I'm James Maxwell, and I'll be running you through our solution number 2 of rerouting the tee box. And I'll also be covering the management strategies and the cost analysis of this project as well. So coming into management strategies here, if you follow along on the diagram, it'll show a rough plan of the new cart path position with some rough lengths. And we've broken up, you can see, or first of all, you can see the pre-existing cart path on the right, and then the new cart path is broken up into A1, A2, and A3 just for measurement purposes. That illustrates where the new cart path will be built to give access to a different entrance point to the tee box. So as we break down the costs of the gravel and asphalt layer of the cart path, we start with a total square cubic yardage of 25 yards. So working that out to $20 a yard brings our gravel cost to $502. And asphalt has quite a large range depending on who's we are contracting out the work to, as we can't do that in-house, but that's roughly $80 to $160 per cubic yard, which brings our cost to $2,008 to $4,016.
Hello everybody, my name is Corbin Schreiner and I'll be covering the agronomic solution for this part of the presentation. I'll be covering the resizing of the tee deck as well as aerating, top dressing, and overseeding. In order to solve this issue, I have split the solution up into two parts, part A and part B. In part A, I took off a negative amount of 50 square feet from the back right corner. This is going to be the corner that's going to be grown into a rough scenario, allowing the grass to both strengthen and become better resilient against drowning. Part B of the scenario is in dealing with the actual drainage part. So if we aerate with hollow tines, take away the cores, allows us to top dress, which reduces the compaction of soil over time. Then we can overseed it with a seed that thrives in more saturated areas. Seeding with a cultivar of fescue or Bermuda will give us a better chance of growing because each type of grass has a better resistance to more saturated areas than others. Allowing this area to grow with seed will give us the opportunity to slowly cut back to the original shape of the tee deck.
In this section of the presentation, we'll go over the Hugoutt equation, what numbers we got, the equation itself, and our final product. The Hugoutt equation consists of D equals 4 times K times H squared divided by S squared. D is the drainage rate at the top of the free water zone at midpoint between the drains in inches per hour. The 4 is the distance that the water has to move from midpoint to the drain. It is not S, but rather 1/2 S. K is the hydraulic conductivity of the soil, inches per hour. H2 is equivalent to HA times HB. HA is the height of the saturated free water zone in the soil. This is the component that relates to the pressure that is being exerted by the head of water above it in the soil. HB is the height of the saturated free water zone which the water has to pass through to move laterally. S squared is equivalent to SA times SB. SA is the distance between drains in inches, feet, or meters. This is the distance which, when divided into HA, gives a gradient on which the pressure of the head is calculated. SB is the distance between the drains. This is a component of the area over which the water was collected. In our instance, we acquired that K was 32.8 inches per hour, H squared was 24 inches, S squared was 78.7 inches times 258 inches. That leaves us with 3,148.8 inches per hour divided by 20,304.6 inches, which makes it so D is equal to 0.155 inches per hour.
In conclusion, our proposed solutions to improve the tee box in case study 6 are designed to target different potential root problems that this tee box is potentially having. As there are some assumptions that can be made from the picture, we determined two main issues of potentially inadequate drainage tile to replace as well as a water saturated zone being fed from the hill behind the retaining wall, and or high compaction due to lots of traffic at the entrance. Obviously, in a real life scenario, we would find the true root problem and find the best solution for that. However, we believe our proposed solutions definitely offer a good solution, and on their own or in conjunction with one another. I just want to thank you for your time in watching our presentation, and please refer to our bibliography for any sources.